Okay, so Ian's going to talk about direct imaging of newborn planets.
Okay, that working? Yeah, cool. All right. Good morning, everyone. My name is Iain Hammond. I'm a third-year PhD student here at Monash. Supervisor is Daniel Price. I'm also supervised by Valentin Christians, who used to be at Monash University and is now at the University of Liège. As a brief disclaimer, I'm heavily on the observational side of things, so I don't have too many models. However, I do have a couple, which I will show throughout this presentation. So I study the direct imaging of newborn planets, and sort of the reason that we want to look at protoplanetary disks is because planets are sort of most luminous during their formation. And on top of that, light from their host star is basically at its dimmest during the protoplanetary disk phase. So the contrast between an exoplanet and its star is actually the most optimal during formation. So this gives us the best contrast during observations. They're also very young, between 0.1 and 10 million years old, which is sort of a region of the parameter space that you cannot probe with methods such as transit and radial velocity. And we can also get orbital constraints by directly observing protoplanetary disks with an embedded planet over several years. We can watch as their orbits change. And we can also look at disks at different ages to get an idea of do planets just form in place and then not move. Migration process is important. And what else could impact orbits? And of course, there is the satisfaction of actually imaging a disk with an embedded planet is very, very nice as well. Finally, there's this nice plot from Christoph's PP7 chapter, which sort of gives a distribution of all sort of detected exoplanets in grey, and you can kind of see this sort of bias in transit and radial velocity techniques towards low separation, sort of moderate to higher mass planets, whereas imaging can give us access to planets that have higher mass and a further separation from their star, which is very, very important for obviously understanding what are the possibilities of exoplanets. So over the course of my PhD, I've been gradually reducing scattered light data from the SPHERE instrument at VLT. So what you're basically looking at is light that has come from the central star and has been reflected off small dust grains on the surface of a flared protoplanetary disk. And you can see that sort of none are the same. They're all very, very different. Some have large spiral arms, one spiral arm, two spiral arm. Others have like gaps, annular gaps, and others have sort of a large central cavity, like down the bottom left here. And all these are sort of, from theory, these are signposts of the presence of an embedded planet or a companion. And you can also go to the disk midplane, thanks to ALMA. So these are, I think, 1.3 millimeter grain distributions from 4 disks in the MAPS large survey. And you can also see the same structures in the disk midplane. You see these beautiful annular gaps, which could be signposts of planets. And you might say, well, where are all the planets in these pictures? So unfortunately, planets in their disks are heavily embedded. So usually that means that they can be enshrouded in a large amount of gas and dust, which contribute to extinction and make them actually more difficult to detect. And then circumplanetary material can also contribute to extinction as well. There's also the issue of contrast. So like I said before, the brightness of a planet compared to that of a star can be sort of 10 to the 6, 10 to the 8, which is difficult if the light from a star is just enveloping that of a planet. And these are also very small separations in the sky. So talking like 0.3 arc seconds for our observational astronomers out there. So there's only very few telescopes in the world that can actually resolve a planet from that of its star. Fortunately, in 2018, on the right, we had the first detected protoplanet inside of a protoplanetary disk, which was amazing. That told us that detecting planets in disks is possible, and it can be done. There was actually 2 planets in here, but they didn't quite know at the time. They weren't sort of convinced. So that was very nice, 2 bedded planets. So during my PhD, I wanted to increase this number. I wanted to find some more. And one of the systems that we looked at that showed promise is called HD 169142. So this is a scattered light picture, again, small grains on the top of the disk. And you can see that it's sort of distributed into 2 rings. We have this, is my cursor showing? Yes, it is. We have this sort of first bright ring, followed by this depleted kind of gap where there is not much dust, then followed by like another ring. And this picture has already been published. I did not actually reduce this myself, but at the time we kind of noticed this little blob sort of in the top left here, which was inside the this sort of depleted area. And in theory, we should know that a planet could carve a gap there. So I've made a little model. This is just based off something we made in a Zoom whiteboard one day of what could be going on in HD 169. We sort of inferred there might be one planet sort of close to the star to make this sort of ring here, and then another one slightly further out to deplete this gap. And then that planet would also be exciting a spiral arm, which could be leading to this over brightness to the left. It's a bit hard to see on the screen, but it is there. So we went to reducing a few data sets from the sphere instrument at VLT. So these are in the near infrared wavelengths. And basically what you're looking at is on the left, the same picture again, and then in the middle and the right is essentially thermal infrared emission between the 1 to 1.6 micron range. And what was very, very nice is our little blob was back across 2 years of data sets, and we also recovered the spiral wake, or what we think was the spiral wake from the planet. And if I play my video, we had 3 data sets taken over 4 years. We reduced them all the same, and they sort of increase in quality. The 2015 was the lowest quality one, 2017 was a bit better, and then 2019 was a little bit better. And so this thing was moving, right? So that was good. And you say, well, Ian, that might be an artifact. So if you make a Keplerian motion plot, we can see that this thing follows very, very, very satisfyingly expected Keplerian motion for a planet at 37 AU, inclined 13 degrees to the orbital plane. Sorry, yeah, from our field of view. And what was also nice about this is you could independently confirm the mass of the star. So it was expected to be about 1.8 solar masses. We got like 1.8 as well, which was good. So from here, we've actually submitted a paper claiming the confirmation of HD 169142b, which raises our number of detected exoplanets to 3, which is very, very nice. So we're at a phantom workshop, so let's talk about phantom models. This one here was made by Claudia, who is giving a talk tomorrow, Friday. And in this model, we have 2 planets actually. There is one sort of in here, which has been blocked, and there is also another in the about 37 AU, which is what we expected based off the observations. And so we're able to get most of what we observed. We got the bright ring. We're able to get to start depleting a gap. This is only run for 500 orbits, so it didn't completely deplete the gap. And we're also able to get the small spiral arm to the east, which was nice. So I think the sort of next step is that now we know a little bit more about the system to continue running the simulation and try to get it as close as possible to what we got to observations. So moving on from HD 169, I also studied CQ tau for about a year of my PhD. So this is another disk. This is quite massive and has a huge spiral arm as you can see again in scattered light. This huge spiral up here, and then lots of smaller arcs. And there's also some shadowing effects. You can see the bottom of the disk is sort of significantly dimmer than the rest of it. And here, the ALMA, we could with the gas, we could also see a depleted region, which could be indicative of creating a planet or a companion. And also in the dust, we saw the same kind of story, 1.3 millimeter dust, a highly depleted region. So we thought, well, let's see if we can find something in CQ Tau with direct imaging, see if we could confirm a planet or is it a companion. Long story short, we looked at 5 data sets. We did not find a clear planet detection, unfortunately. So likely it is, if there is a planet in there or a companion, it's too close to the star for us to be able to resolve. But what we could infer was that the star has a very, very high radial velocity in the Gaia data release 3 catalog, which was kind of interesting, significantly higher than any other disk that we've ever looked at. There's also very highly non-Keplerian disk kinematics, which could be indicative of a perturber, a massive spiral arm, obviously the depleted cavity, and these shadowing effects. So what we inferred was this could be a binary situation. We know that lots of stars form in binaries, so it sort of made sense. So we made a model. This is just like our first go. Observation on the left, scattered light again. We used Phantom and then MC-FOSS to produce a synthetic image at the same wavelength. And we used an inclined and eccentric companion with 0.2 solar masses. This is very big. And we're able to get a reasonably good match. We got a lot of the spiral arms up here, a lot of the small little arcs. We got a depleted cavity. And we also got some of the shadowing effects from the inclined inner disk, which is sitting around the central star. Unfortunately, we haven't quite matched the shadows yet, just to the precession of the inner disk. So that's sort of our next step to improve this model. Yeah, for my conclusions. So, well, direct imaging is so far been quite hard to find planets, but it is possible, and we are starting to get some coming through. We made a new discovery, HD169142b, and as you can see, our models can help us sort of understand and interpret our observations, see what is possible. Does our story sort of match theory? And then those observations can also inform models again. I will leave it there and we'll take questions.
Thanks for the interesting talk. Does anyone have any questions?
Thank you for the nice talk. So do you think that high resolution dust observations of HD16 could show the possible circumplanetary disk?
With ALMA?
Yeah, with ALMA. Sorry.
Yeah, we think it's possible. So we haven't determined whether with ALMA if it's actually possible to be sensitive enough to that CPD. You may need a huge amount of hours in order to be actually able to detect it. Like it should be there. We haven't run the numbers. We're chasing it with JWST instead. But yes, in theory.
Thank you.
Hi, thanks for the talk. I was wondering, in the model you showed where there is an unseen companion, did you try different masses? I mean, what are the constraints, observational constraints on the mass?
Mm-hmm.
And have you tried different masses, and how do your results depend on the mass of the unseen companion?
Yeah,
comment
yes.
on that?
Sorry? Oh, yes. So we tried quite a few masses. We started with a planet at about, what was it? Something like 20 AU. So somewhere like out here to sort of help excite some spiral arms, deplete the cavity. And what we found was that just a planetary mass was not sufficient enough to be able to cause all of the features in the disk. So we couldn't make big spiral arms. We couldn't make such a huge cavity just with a planet alone. We did something bigger. So then we went up to about like 20 Jupiter masses, and then eventually we did 0.2 solar masses, and that's what got us to that. Observationally, we were able to sort of infer that we should have been able to detect, like if there was a planet, say out here, around 3 to 5 Jupiter masses. So at least we had strong constraints that there shouldn't be a planet outside of the spiral arms. It has to be something in here that is causing the disk features.
Just a last question: does your cavity become eccentric at some point, or it remains fairly circular, like the one that you are carving there with your inclined?
So that's a mask. That's
Just a
just
mask,
to,
okay.
that's just to replicate the chronograph.
Okay.
This, yeah, because it was taken with a chronograph. Yeah.
Okay. Thanks.
If there aren't any more questions, let's thank Iain again.